to stop. So we talked about R squared as a measure of regression fit, how well the line fits the data. There's another measure that you'll come across, which is called the standard error of the estimate. And just like R squared, it's a measure of the accuracy of predicting Y using X. But whereas R squared is always between 0 and 1, it's a kind of a normalized quantity. The standard error of the estimate is in the units of Y, whatever that is. So that makes the standard error of the estimate a bit more easy to grasp. It's a bit more easy to understand how well the model fits because it's in the units of the thing being predicted. So here's the equation for the standard error of the estimate. It's the sum of each observation minus the predicted value, so those are the residuals, squared, divided by the number of data points, all square rooted. Now, sigma EST, that's a Greek sigma, that's the notation we use when we're talking about the population value. When we're talking about a sample of data, the notation is S, and then EST, and the equation is slightly different. For a sample, the standard error of the estimate is still the residuals on the top, squared, sum, but on the bottom it's n minus 2 instead of n. And you're going to come across this phenomenon in stats for many different statistical measures. The idea that when you're developing an equation for the population value of some statistic, it looks one way, and when you have to use it on a sample of data, it's slightly different. And it's usually that wherever there's an n, you have to subtract some number when it's a sample. And I don't want to get into the gory details of why that is. It has to do with the fact that when you're dealing with a sample of data, it's a smaller number of data points than in the entire population. And when you use the population equation on a smaller number of data points, you can get a bias in the estimate. And to eliminate the bias, you have to tweak part of the formula. That's the short explanation. So it's the sum of squared residuals over n minus 2 square rooted, and that gives you the standard error of the estimate. So here's an example where we're predicting weight in pounds from height in inches. Here's our line of best fit. R squared is 0.77. That's pretty reasonable. That's reasonably close to 1. And you can see the data points don't depart hugely from the line, although some of them are not so great. And in this case, if we compute the standard error of the estimate, we get 14.11 pounds. The units are in the same units as the Y variable. So, whereas for R squared, we have to look at 0.772 and sort of think, that seems okay. That's pretty good. Is that good? I don't know. Is it good? Sort of close to 1. What does it mean? With standard error of the estimate, we get a value in the same units that we're trying to predict. So what this essentially means is when you're trying to predict weight from height using this model based on that data set, the typical error you're going to get in your prediction is 14.11 pounds. It's not quite exactly equal to the average residual. It's more meant to represent if you use this model on new data from the population many times, then on average you incur an error in your prediction of about 14 pounds. So now you can sort of determine for yourself, okay, is that good? Is that bad? If I'm trying to predict weight for whatever purpose and the average error is 14 pounds, is that good? Is that bad? If you're marketing a new bathroom scale that you want to sell to people and the average error is 14 pounds, maybe that's not so great. Maybe you want to improve your technology. If you're trying to estimate the weight of humpback whales from, satellite imagery, and the average error is 14 pounds, that's probably pretty good, because they weigh a lot.
So if you want error of 14 pounds for every value, or is it across all the values?
It's more to me, it's sort of across all the values. And it's meant to be a measure that's not literally based on it. it's not meant to be the error of this data set in particular. It's meant to represent, if you use this model on new data that you acquired from the population many, many, many times, what would the typical error be? And it's telling you it would be based on the data you have and the line you fit, then if you got new data, the average error would be around 14 pounds. Okay, so we've got two measures of model fit. R-squared, that varies between 0 and 1, and standard error of the estimate, which gives you a measure of model fit in the units of y, which is arguably more useful. We already talked about prediction when you have the model equation, so I'm going to skip that. You can look at those slides on your own. Another way of characterizing the precision of estimates is to use confidence intervals. Did you cover confidence intervals in 2811? Yeah? I see them like, oh, yeah. I know. It's a bit of a weird concept. So you probably looked at a 95% confidence interval on some estimate. Before we look at confidence intervals of a regression model, let's just very quickly review what a confidence interval is of a mean of a sample, a really simple example. Let's say you have a sample of data. Let's say I measure everyone's height in this room, and I compute an average. What's the confidence interval on that average height? The confidence interval of the mean of a sample is this, I guess it's a medium ugly equation. It's the average value, that's x bar, it's the average value, plus or minus this thing times that thing. So that thing is the standard deviation over square root of n. And this thing is the t-statistic with 0.975 percentile and n minus 1 degrees of freedom. That's a number that we used to have to look up in the back of a textbook in a giant table. And now we can just use R to give us the value. So if we have some data here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values of x, we can compute the lower confidence band and the upper confidence band by taking the mean of x plus or minus. This QT gives us this thing, and this part gives us that thing. And the bottom line is we get a mean, and we get these two values that bracket the mean. The mean of the sample is 66.7, and the 95% confidence interval is 59.98 to 73.41. So if we ever have a mean of a sample, we compute the 95% confidence interval around that mean. Now, what does that actually mean conceptually? What is that 95 confidence interval telling us? We computed the mean of the sample. What does the confidence interval mean? I mean, we have the mean. The mean is 66, so what do those refer to? Yeah.
Means that 95% it means that we get the same answer with 95.
I know, it's hard.
It's tricky.
It is very tricky.
You'll use it, something to do with the method, and if you use that method, you'll get that answer 95% of the time.
Yes, sort of, on the right track. You have to think both of the concept of the sample and of a population. So, yes, you're next.
So is it that we're 95% of time confident that our answer like within the determined area?
Yeah, so the answer was, is it that we're 95% confident that the mean actually lies between those two things? Almost. Not quite.
Is it that if we were to take like a data point in our statistical model, we would have 95% confidence that it would appear between those two values?
Yeah, so the answer is if we were to take a point in our model, this would mean we have 95% confidence that it lies between those two values. Almost. This is something that actually I didn't know how to say it properly until I had taken, I don't know how many, 4 stats courses or something. Because in fact, I'm positive, the first 2 profs I had teaching stats explained it wrong. They said the wrong thing. It's actually not that you're 95% confident that the mean lies between these two values, but it's close to that.
Isn't it that you're that percentage confident that from the null hypothesis, like it's not because of an error?
Yeah, so the answer is it that you're that percent confident that because of under the null hypothesis, it's not an error? Some kind of, sort of, something like that. Yes, maybe. Kind of, yeah. So the key thing to remember is that this is the mean of a sample of numbers. And the idea when we do statistics is we want to know something about the world, how the world works. We want to know something about the population. Now, if the population I want to know about is everyone in this room, and I want to know, are the male students in this room taller than the female students in this room? This is the population. Then I don't need statistics. All I need to do is literally measure the height of all of the male students, measure the height of all the female students, and compare them. And if this is bigger than that, then I have my answer. I don't need statistics. Right? That's the answer. If my population is all humans, and I want to know, are male humans taller than female humans, then the only way to avoid statistics is if I go and measure the height of every male human and every female human on Earth, which I can't do. So what we have to do instead is take a sample, presumably a random sample. And so if we take a random sample from a population, and we're trying to estimate the average value of that thing, whatever that is, then we can take the mean of the sample, which here is 66.7. And that's our best estimate of that value in the population. Right? We've just taken a random sample and we've used that to estimate the population value. So that's our best estimate of the population value. And the 95% confidence bands tell us something about the precision of our estimate. What we want to say is that means that we're 95% sure that the population mean falls between those two values. That's what we want to say, and it's not quite right, unfortunately. It's close. The right answer, the real answer, is the following. If we were to take more random samples, we were to take 100 random samples from the population, and each time compute a mean of those samples. And each time, no, how does it go? Oh man. If you took 100 random samples, and each time you computed a 95% confidence band for that sample, then 95% of those confidence bands would include this value, and 5% of them wouldn't. It kind of looks like this. We took one sample, like let's say that sample. Well, let's choose a better one. We took one sample here, and that circle is the mean, and that's the confidence, 95% confidence interval we got. If we had done the experiment 99 more times, and taken 99 more random samples, and each time computed a mean and a confidence band, then they might look like this. And 95 out of 100 of those confidence bands would include the real population mean. And 5 of those 100 would not include the real population mean. That's the way it goes. The real population mean is actually unknown to us. We don't know what it is. So the 95% confidence bands are related to the precision of our estimate. The catch is, we did this experiment once, not 100 times, and we don't know which of those 100 hypothetical times we include the population mean or not. Our one experiment might be this one, where we don't include the population mean. But the width of those confidence bands tell us something about the precision of our estimate. It's bad. It's confusing, and I kind of flubbed it up a little bit. Let's leave it for now. So the point of bringing up confidence intervals again is because we can calculate them for not just the mean of a sample. We can calculate them for the parameters of our linear regression model. Our linear regression model estimates two quantities. We estimate a slope, and we estimate a y-intercept. The y-intercept is beta 0, and the slope is beta 1. So these beta variables, beta 0 and beta 1, they're parameters of a model. Just like the mean of a sample is the parameter of a model. If the slope is 0, then beta 0 is the mean. So we can compute 95% confidence intervals for those parameters as well. In R, it's easy. We just use the command const_int, and we pass it the model object that we got when we did the ln command. And we get output that shows us for the intercept, the lower and upper confidence intervals, and for the slope, the lower and upper confidence intervals. So the sort of general way to interpret them is if the 95% confidence interval for your slope includes 0, the lower one is negative and the upper one is positive, then you don't actually have a lot of confidence that your slope is not 0. Is the way to interpret it. So let's leave the definitions behind for a second and look at an example. Well, we already looked at that example. You know what? Let's leave confidence intervals because I don't like it as much as you don't like it. We have just a couple things to do before we end. We have hypothesis tests, p-values, and we have the assumptions of linear regression. So let's quickly talk about hypothesis tests. When you run the ln command, I showed you how to get the coefficients of your model. If you use the summary command and you give it your model object, you get this big output that shows you more information. It reminds you what the formula was that you used for your model. It gives you the minimum and some quartiles for the residuals, which gives you a general idea of how the model is fitting. You get the estimates for the intercept and for the slope. Intercept is labeled intercept, and the slope has the same label as the name of the x variable, x. You get the standard error of the intercept estimate and of the slope, and you get a t-value and a p-value, a t-test and a p-value for the intercept and for the slope. And you also get an r-squared. We talked about r-squared, and you get an adjusted r-squared, which we'll talk about next time when we talk about multiple regression. But for bivariate regression, this is the r-squared of interest. And then at the bottom, you get another statistical test. You get an F statistic and a p-value. So what is that? What is this test? What hypothesis does this actually test? Now, if you notice, if you're attentive, you'll notice that this p-value here looks the same as that p-value there, even though that's a t-test and that's an f-test. It's the same p-value. And for bivariate regression, it is the same test, in fact. This test at the bottom, it's called the test of the model as a whole. And what it's a test of, it's a test of the model you're actually fitting, which is called the full model, versus another model that you didn't test, called a restricted model, in which there's no dependence of y on x. So the test of the model as a whole is comparing your model that includes a slope and an intercept to this other hypothetical model called a restricted model that does not have any slope, or to say differently, in which the slope is 0. So that horizontal line is only an intercept. So that test of the model of a whole is saying, how much better is your model with an intercept and a slope than a model that just has an intercept? You fed a line to your data that has an intercept and a slope. Your line is tilted. How much better is that than a model where the line is just flat? Do you really need that slope? Or are you just spending too much statistical money? Can you just do as well by just having a horizontal line? If a horizontal line is just as good as a line with a slope, that means there's really no dependence of y on x. So the full model has beta 0 and beta 1. And the restricted model, as it's called, has beta 1 equal to 0. So it's basically gone. And it's just testing the model where y depends on a constant. It doesn't depend on x. Y just has a mean plus some random errors. So that's, in fact, the same concept and literally the same test as the one that's lined up with the slope variable here. These tests that appear here next to each parameter are basically a test of whether that parameter is reliably different than 0. And so here the p-value, it's the same p-value, and it's really, really tiny, 0.0000818. So that's definitely statistically significant, which means you have a lot of confidence that that slope is not 0. So what can anyone articulate, what is that the probability of? It's the probability of what?
Of making a type 1 error.
The probability of making a type 1 error. No, not quite. Not quite. The probability of a type 1 error is whatever alpha level you decide is the one that you're going to reject the null hypothesis at. So if you reject the null hypothesis if p-value is less than 0.05, then 0.05 is the probability you'll make a type 1 error. But this probability is something slightly different. Yeah?
It's like the probability that it's due to random chance.
The probability that it's due to random chance. Yes, you're much, much, much closer. That's almost it. Yeah?
Is it the probability of making a type 2 error or rejecting the null hypothesis when it's true?
The probability of making a type 2 error? Not quite. No, you were closer. So it's the probability that you could have ended up with a slope estimate this big in your sample if the true slope out there in the population is 0. So if the null hypothesis is true, the null hypothesis is always that nothing's happening, that everything's random, life is chaos. The null hypothesis is that y in the population does not vary with x in the population. We've taken a random sample of x and y, and we've gotten fooled by random chance. We're so unlucky that our random sample makes it look like there's a relationship between x and y. And what's the slope of that relationship? It's 2.6 in our sample, even though it's 0 in the population. If that were true, then this is the probability that that could happen. That we could have ended up with a sample this big, with a slope this different than 0 if it was actually 0 in the population. So the fact that that probability is really tiny means we have to make a judgment now that relates to what you were saying about type 1 error. So that's the probability. It's not 0. It could still be that the slope in the population is 0. And that we're being fooled by we just happen to take a random sample that makes it look like there's a relationship. What's the chance that could have happened? 0.0008. That would be 8%, 0.8%, 0.08%. 8 in 10,000 times. That's a tiny probability. So now in inferential statistics, as a scientist, that's the data. There's a tiny chance this could have happened if the true slope was 0. So now we have to actually decide something. Okay, so what does this actually mean? Is the slope? Are we going to say the slope The slope could be 0. We're going to write our nature paper. There might not be a relationship. No, we're going to say, that probability is so small, I don't think that's what happened. I'm not that unlucky. We took a random sample from a population, we estimated the slope. Our estimate is 2.6. The chance that that could have been just due to random chance is so small, I don't believe that happened. I'm going to accept the alternate hypothesis, reject the null, and plant my flag in the ground and say, that is the actual slope between x and y in the population, even though it's just based on our sample. Now, type 1 error relates to, this is a probability of 8 in 10,000, 0.0008. So imagine this is a really tiny probability over here, and then as we walk along here, the probability gets bigger. So 0.008, 0.008, 0.009, 0.06, no, I'm going the wrong way. 0.03, 0.04, 0.05, 0.06. 0.05 is usually where people draw the line in the sand and say, if the p-value is less than 0.05, I'm going to reject the null hypothesis. If it's greater than 0.05, I'm not going to reject the null. If it's greater than 5%, that I could have gotten a slope this big, even if the real slope is 0, I'm going to say, I can't really say that it's not 0, because 5% is big enough that it could have happened. 4%, right in your nature paper, it's 2.6, it's not 0, right? So that line in the sand, that 5% line in the sand is what determines actually how much type 1 error you make under the null hypothesis, which is counterintuitive. How can just be what I decide in my brain is the line in the sand actually determine anything? But that's the way it works. The actual p-value doesn't tell you what the type 1 error rate is. The type 1 error rate is how many errors would you make if you did this experiment a bunch of times and the null hypothesis was true. All right, we got deep into p-values, but that's what this test is. The test of the model of the whole, a test of the model as a whole in bivariate regression is the same as the test of whether the slope is 0 or not. And if a p-value is small enough, we reject that idea and say the slope isn't 0. I'm really confident the slope is not 0. What is it? Well, I don't know, but the best estimate is from my sample, 2.6. So obviously the value of the slope is going to be related to r squared as the standard error of the estimate. The more slope the line has, the stronger the relationship between x and y. We talked about that.